Okay, I've asked Kyle to lead the recitation on for homework problems, and let's talk about that. Other questions are fair game as well. And then I'd like to review the quadrature at the end if we have time. Take it away, Kyle.
Am I taking it away?
It's all you.
All right. Good morning, everybody. How are we doing? How's the homework coming along?
So should we give the students that are enrolled a chance first to ask questions, or is it just free for all?
I don't really care. They're capable of speaking up.
So I have a question. If we could just look at, and I think you're going to review this a little bit, Michael. Maybe this question isn't necessary, but on the third question for the most recent homework, it's kind of like I think it's saying the same thing that original homework questions were saying in the first one. I didn't get it then, still don't get it now. But it's saying verify the accuracy of the 3-point Gauss-Legendre quadrature rule for monomials 1 epsilon epsilon squared in turn. First question is, how high does it want us to go? On question 1, we went up to 10. So we could go up to 10 in monomials. But are we only supposed to go up to squared? It has a dot, dot, dot. So we could go forever.
Yeah. So I would go up to quintix at the largest, so 5th order.
Okay.
Because I believe that's how high you can go for a 3-point quadrature rule before you start losing accuracy.
So my second question to follow on with that is, in terms of the accuracy of this Gauss-Legendre quadrature rule, so is what we're doing, I found the equation for the summation from I equals 0 to n of the function f such that you're inputting epsilon I and then multiplying by the weight wi. And so here's where you have these points, epsilon and w, and you can put those points into the function, right? And then your function is, like 1 x squared, x cubed, so on and so forth.
Mm-hmm.
And so if you're just going to be plugging these weights and epsilons into that function, the summation, why is it that we're summing it? Like, it would make sense to me that you're kind of putting the epsilon in for your x value. You're putting that into the function of f, and you're weighting it by w for each one of these points. So you're not really querying the function at every possible point. You're only querying it at these defined points.
You're very special, Eric. Very special points.
Very special points. You're
How about hold on to that question, because I rewrote all the quadrature stuff. I'll go through the
okay
material and it will answer that question.
Okay. I can hold off on that question then. That's what I was wondering. I didn't know what part of that you're going to go over. So if you're going to go over that, great.
Okay. So was there more to your question on question 3 beyond that?
I think I'll just wait for Mike to go over what he's going to go over and throw my questions at him. I'll give everyone else another second. If they don't ask, I have a couple more questions.
Okay.
I really like your questions, Eric, because it's very hard to, as a student, I have a hard time explaining what I don't understand because I don't understand it enough. For the second set of, let's see, not this homework, but the previous homework, I was having a hard time getting number 1 and number 2 started.
All right, let me pull those up. Let's see. This is the second set.
Yep.
So these guys right here.
Mm-hmm.
Okay.
Okay.
Go ahead.
Let me move that out of the way. Okay, so you're trying to figure out how to get started on these problems, correct?
Yeah.
Okay. Are you writing, Mike, or?
Yeah, I can write as you explain.
Okay. So on the first problem, what you are trying to do is you are trying to approximate the vector f with some vector that lives inside the xy plane. Does that make sense?
Mm-hmm.
Um,
So conceptually, I can do it, but using the notation, I don't know how to get through the notation.
okay. So like what notation are you struggling with specifically?
I think it's this notation where KAB is the inner product of NA, NB, or I guess we called that M, didn't we?
Mm-hmm. It's like I don't know what to make NA and NB.
Okay. So M B equals F, right? This is our problem.
Mhm.
And we need to fill up M and F and then solve for D. That's what we're after here.
Right.
M is equal to okay. So
Mike,
M,
you're taking over again.
I know. But Kyle, do you have anything to write on?
I don't really have like a nice pen, like the nice pen or anything like that,
Okay.
like
Well,
you do.
we'll consider this to be a tag team event then.
Okay.
Okay.
Yeah. So, so Rebecca, the ends there, that's what kind of the notation that we use to say the basis of our problem in general. Like for generally, that's the kind of notation that we use. But for these problems specifically, it's the e's that we're using for our basis. So the basis that we have that spans the XY plane is the E1 and the E2 vectors, like Dr. Scott wrote up there. And so those are the vectors or the basis that gets plugged into that inner product.
So you wouldn't use a 3x3, you'd use a 2x2?
A 2x2, correct.
And
Because
then
you're trying to approximate F with a combination of E1 and E2.
mhm.
Let's just do a few of these. So let's start building up our matrix MAB. Okay, so what's the appropriate inner product, Rebecca, for R2?
For R2, it's E1 dot E1.
Yeah, so it's just the dot product that we're using in Rn, right? So E1 dot E1 is what?
It's 1.
Okay,
So this is the identity matrix.
that's exactly what it is. Let me just write down what the entries would be. That's 1. That's 0. And this should tell you exactly why we like orthonormal bases, right? These basis functions, they're orthogonal and they have unit norm, orthonormal. And this is why we like it so much, because E1 doesn't have any component in the direction E2 and vice versa. They're completely orthogonal to one another. Okay, so there's your M right here. So let's build up our F. Okay, so what's the first entry in F going to be?
So the first one is E1 dot F, and so that's going to be 1.
Okay. And E2 dot F is equal to 1. All right, so now, can I erase this, Rebecca, or do you want me to get? Okay. Okay, so now we have basically the system 1001 D1 D2 is equal to 1 1. So this is our M D. So this is like the easiest possible problem that I could think of for this particular, you know, this projection idea, right? Because you've got an orthonormal basis, you're in R2 and R3. And so what happens is that the mass matrix becomes the identity.
Which
So
the inverse of the identity is just the identity.
Right? So essentially what that implies is that D1 is equal to 1 and D2 is equal to 1. So the solution UH is the vector 1 1, which shouldn't be a surprise. That's the projection of, you know, if you think of just about what we had here, we had this F, we basically projected this guy, right? And it's 1 1, the components of that vector.
Mike, can I make an important comment?
I was going to do that too. You go, Chris.
Go for it, yeah. Yep. Is the comment coming?
Flying D1 2 times your second. It's really easy to miss that.
Hey,
Like-
Chris, you have to start over because we couldn't hear you for the first part. At least I couldn't. The other people could.
Yeah, I couldn't.
Can't hear you again.
Maybe Caleb, do you want to do the talking?
Yeah, I'll make Chris's comment for him. It's interesting here that the D vector, in this case, actually corresponds to the spatial coordinates. So UH is the same as D, but it's important to note that that's not in general the case. That's because of our basis. But in general, UH would be D1 times E1 plus D2 times E2. So the D's are not necessarily the spatial coordinates. They're just the coefficients for the basis vectors.
And that's what you'll see in the next problem, because we'll pick a non-orthonormal basis. So it'll be the same vector, but these components will change because the base vectors change.
So question, how do you, let's see, earlier you were, for the F matrix, well, F part, you're dotting E1 with F and then E2 with F. I was worried that you'd have like 3 terms instead of 2. Like
Yes.
E1.
You just take the minimum dimension. I mean, the dot product is just the sum of EI, FI, right? And so if FI has 3 components and EI has 2, then this just runs over 2.
Okay.
Yeah, because it's like saying that basically it's equivalent to saying that you're dotting EI, but then you add a 0. Is essentially there's no component in the third direction. That's the exact same thing.
Okay.
Yep. Good question.
So my question about in the same right here, where in this equation as defined, the problem, does it dictate that E1 is supposed to be part of R2? Because
Yeah,
it tells us to find the best approximation UH, which is in R2,
it says
and
note
then F, which is in R3.
in the problem, it says, note that in this case, we have chosen the canonical basis for Rn. That's what that means.
Canonical basis for Rn.
Yeah, the canonical basis is this orthonormal. But I could definitely come in here and specifically say that the EIs are in.
Because it looks like to me the EIs are in R3. If F is within R3, EI would need to be in R3 as well. So I'm kind of wondering why you
Well, that's
wrote.
what this statement says. It says, note that in this case, we have chosen the canonical basis for Rn. So if n is equal to 2, we're using the canonical basis for R2. If n is equal to 3, we're using the canonical basis for R3. So this F comes from R3, so this is the canonical basis for R3. This UH comes from R2, so we're using the canonical basis for R2.
So we could call these E1s and E2s different things, potentially, because they are the basis for R3 and R2.
Sure. Yeah, I could come in here. I'll come in here after class and make this more, I guess, less ambiguous.
Yeah, because I'm just looking at this as what you've just written. UH equals D1 E1 plus D2 E2. Those are different E's than the E's that are making up F.
I guess the point is that really what I'm also telling you is that you should be able to read this and just know from context what I'm saying when I use that language.
Sounds like I need to go back to school then.
I think part of the confusion comes from you also need to recognize that R2 is a subset of R3. And so that there's kind of some implicit throwing away of components going on there.
Okay, good. Yeah, I'll come in here and see if I can.
Yeah, it's kind of like, to your point, Kyle, it's kind of like saying you've got some function, right, in X, Y, Z, right? And then, so then when you say projection down to like the X, Y plane, right, those are still like this, they're still like the same X, Ys, right? They're like that subset of X, Y, Z, right?
Correct.
I don't know if that's a helpful, Eric, a helpful way to think about it.
So at the end of the question, it says, show that error in your computed solution is orthogonal to R2.
Yep.
That's, when you try to calculate that, you'll be doing a dot product with a vector that's size 2 and a vector that's size 3, right?
Uh-huh. Yeah, same thing as I described earlier.
Okay. Cool.
So do you see how to go about problem 2 now, Rebecca?
Yeah, that clarifies the rest of, problem 1 and problem 2. And since the others are based off of that, it should help with everything.
Okay, great.
Thank you.
So what else can we help people with? What other problems have come up?
Thank you.
Did everybody else get everything figured out exactly?
I have a quick question, Kyle.
Okay.
So I asked this question to Chris earlier, but I'm not entirely sure if I understood exactly what he said. So, Dr. Scott, could you go up to the top of the page by any chance to the minimization problem that we're solving? So speaking like in terms of units, right? Like, I don't know, like in physics, you wouldn't ever subtract like a velocity vector from like an acceleration vector, but I'm kind of curious why we're trying to minimize like the distance between a force vector and a displacement vector, because they have like completely different units, and it doesn't seem really to, I don't know, match up to me.
There's
If that
no-
makes sense.
There's no units yet in this we have not, these are just
Okay.
elements of a space, and we're just using the fact that it's an inner product space at this point.
Okay.
There's no
Yeah,
physical-
correct me if I'm wrong, Mike, but the answer that I gave Kaylin was, once we apply units, you have to formulate the displacement in terms of force. So we call that kind of an internal force, right? Where you're balancing external force with internal force, and that internal force is a function of your displacement.
Yeah, and in fact, if you want to, I actually was quite pedantic in this next one here. So here's the problem we're going to be doing next. And here I show you how all the units work.
Okay.
So yeah, you need to, basically for a unit set, you need like a force unit, a distance or a length unit, and a time unit. Those three guys, everything can be converted. Everything you've ever seen is composed of those guys, and maybe there's something else like a temperature or whatever. But normally you pick units, and then you just have to be completely consistent within the units that you've chosen.
Okay. Thank you.
Yeah, and another maybe another thing to kind of explain what's going on is oftentimes we really just mean the solution, not just and it just has become to mean the displacement, because that's what the problem we're always solving is. So you can just think of as the solution rather than a displacement in these cases. So does that help?
Yeah, it does.
So quick question with number one. If you, let's see, if you did,
You want me to
Mama.
yeah,
Thank you.
sorry.
You want to order something tonight? Okay.
So problem number one on this, if you did the integral, well, yeah, the integral instead of the dot product, would you get a similar result?
It wouldn't make any sense because you can't equip an integral dot product to Rn.
Okay,
So it would have to be like a function space, like L2 or HK. So the inner product has to be appropriate for this space, like they go together as a pair. So if you're dealing with Rn, the canonical inner product for Rn is the dot product. The integral is really something that only corresponds to infinite dimensional places or spaces, because the integral, conceptually, this is really nothing more than an infinite sum. And so in Rn, since n is less than infinity, you don't need the integral. You just need the sum, which is why the dot product in Rn is I equals 0 or 1 to n, right? Because this is what's telling you you're finite dimensional. But otherwise, if you notice, so if we look at the L2 inner product, let's say it looks like f g d omega. So this is
This is really good, Mama.
We got lots.
Someone needs to meet Clinton.
I'm trying, I can't mute him for some reason.
What? Me?
You need to mute
Yeah,
him.
you need to be muted.
Thought I was muted. Sorry.
So what was I saying? Okay, so this is the L2 inner product, which really in some sense is like an infinite sum of Fi-Gi. That's kind of conceptually what this symbol means this. So it shouldn't be a surprise that in Rn, we basically, and we want to do, what's the dot product? Well, it's F dot G. It shouldn't be a surprise then that it looks exactly the same. right? Except just for this n. So that's as soon as you're going to move into function spaces, a function is like an infinite dimensional vector. So that inner product has to be able to deal with the infinite dimensional nature of that, of the vector you're dealing with.
That makes a lot of sense. Thank you.
Yep. That's why RN's usually instructive, because if you know how things work in Rn, and then you go to function spaces that are infinite dimensional, but they have an inner product, in some sense, all of your intuition that you have in Rn carries over to these function spaces because they have an inner product, which gives them the geometry of Euclidean space. Okay,
That's awesome.
any other questions on homework or anything?
Yeah, Dr. Scott, I was wondering if you could kind of help me start off question 2 on homework 3 with the Gram-Schmidt orthogonalization. I'm just kind of struggling to get through the notation a little bit and figure out kind of where to start it off with.
Yeah, why don't we do Gram-Schmidt with a vector first?
Awesome. Yeah, that'd be great.
So if we go, I moved Gram-Schmidt back into the math here. So here it is. So let's say we've got, I don't know, 2 vectors. Let's say all you need to start the procedure is a set of linearly independent but not orthogonal basis functions. So in Rn, let's maybe we'll do R2. Let's pick 1, 1, and what's another one that I should do? Anyone care?
1.
What?
Oh wait, that's orthogonal. 0, 1.
Okay. So we've taken 2 vectors. One of them is like this. Let's call this, what are we calling these? Let's call this N1. We'll call this N2. So this is N1. And then this is N2. Okay, so they're linearly independent, but they're not orthogonal. So we want to run the Gram-Schmidt procedure on these guys to make them orthogonal to one another. So we'll just go through this step by step. So N1 hat perpendicular. Let's just set that equal to either one, N1 or N2. It doesn't matter. Why don't we pick N1 because it'll be a little more interesting. And then N2 perpendicular is going to be 0, 1, right, which is N2, minus the projection, which is the inner product of, let's see, projection N2. So we've got the dot product of N2 dotted with N1 over N1 dot N1 times N1. See how I basically just transcribed this using this right here as a generic inner product. I'm using the right inner product, which is the dot product for R2. Okay.
Just to be a little more clear as to what to do, maybe you should put like bars in the perpendiculars on the N1s.
Right. So this is the N1 perpendicular. N1 perpendicular. Okay, so let's go ahead and do this. Okay, so this is...
You need a square root as well, right?
No square root. Square root.
For the north?
This is a dot product. This is inner product, not a norm. I haven't done this. Oh, you're right. Yep. Sorry. I have one more step on this first line here, which is.
I'm just matching what you have on.
No, you're right. I have one more step here, which is.
Gotcha.
So let's actually plug these numbers in so it doesn't get so messy. Okay, so can somebody compute this? So what's N1 normalized by its length? Should be like √2 something. 1/√2, so it's.
Do you want one of the students to do it? Because I can tell you what it is right off the top of my head.
I think it's this, isn't it?
Yes.
It's 1 over the square root of 2, 1 over the square root of 2. Yeah, that's it.
Okay, so there we go. So now we've got our N1 bar. Let's correct this to be now just. Okay, so now so we're done here. This first line is done. We have our N1, or what's going to be our N1 orthogonal. It is also normalized. So we have our N1 guy here. It's this one right here. And so now we can move to the second line, which is 0, 1 minus N2 dotted with this guy, which is what? N2 dotted with this is 1.
No,
No,
Dr. Miles,
I'm not
Dr.
following
Scott.
now.
What?
I
What's
was
wrong?
also just I was looking at your notation on the left. You still have a N1 bar orthogonal in the projection, yet you've written it as the end product on the far right.
So they're equivalent to each other. It's just that if you put the bar in there, so go down one line, Dr. Scott. So over. So if you put the bar in that term, it's more numerically stable. But if you have exact arithmetic, they're equivalent to each other.
Okay, that makes sense.
Okay, so N2, which is 0, 1, dotted with N1 perpendicular, what is the value? It's 1√2, right? Everybody see that? If you dot these two vectors together,
Yeah.
okay? And then that's going to be over just the dot of these two vectors with one another. So it's 1√2 times 1√2 plus 1√2, 1√2, which is 1. That's convenient, isn't it? And then it's multiplied times 1√2, 1√2. Okay, so what do we end up with? 0, 1 minus 1√2 times 1√2 is 1/2. 1√2 times 1√2 is 1/2. So we end up with the vector minus 1/2, 1/2. So now we've got two new vectors. They're orthonormal. It's an orthonormal set. We have N1.
So they're not orthonormal.
There's one more step. There's one more step. I keep forgetting that last step, which is that we take this guy here and we're going to take N2 bar we're going to take the norm. Can somebody figure that out for me?
Just minus 1 over root 2 plus 1 over root 2.
What's the what is the vector?
Minus 1 over root 2 plus 1 over root 2.
They're not equal to each other. The equality. Sorry.
All right, so this guy here is our second vector in the orthonormal set. So we've got this guy, and then and if you take the dot product, what you should see is that so if you take n1 dotted with n2, what do you get? 0, because they're orthogonal. So there you go. So that's Graham-Schmidt on R2 with 2 linearly independent but not orthonormal vectors. And it generates a set of vectors. It's not unique. I mean, there's a lot of possibilities. Like if you started with, rather than starting with n1, you started with n2, you'd get a different set. But there you go.
So now looking back at problem 2 of homework 3, it says to do this with the power basis. And I guess I'm having trouble. How do we translate the polynomials or the monomials over to kind of this vector format that we're using?
Okay, sure. All right, so let's go look at that. Right, so let's do so here it's the exact same process. Let's figure out what the basis is though first, because I think that's probably what your question is.
Yeah.
So the power basis creates, so our first quote unquote vector is going to be 1. That's our first basis vector, right? It's 1 because it's a function space, right? So it's the function 1. Then x is the next guy, x squared, and so on. And so this will become n1, n2, n3. Do you see it now?
Mm-hmm.
And so when, like, let's just start here. You get like n1 perp is just, let's set it equal to this.
You're not doing this for the Legendre polynomials. You're doing this for just the monomials.
You start with the monomials, and if you use an L2 inner product, it generates the Legendre polynomials. Graham-Schmidt will give you the Legendre polynomials. So then you have n1 perp is just 1. And in this case, so we have a norm here. What's the appropriate norm? So if you're in a function space, and I think I tell you to do the L2 inner product, which is going to be, this is F and G. It's going to be F, G, okay? And so what's the norm? The norm is nothing more than the square root of the inner product. Okay, so if we want to compute the norm of the function 1, we have to compute, so if we want the norm of the function 1, that's equal to the square root of the inner product of 1 with 1. And what's the domain that I tell you to do it over?
There's not actually a domain in the problem.
Okay, that's an oversight that needs to be corrected. Oh, well, yes, there is, because it's the Legendre polynomials, right? Is that what I'm telling you to do? Yeah, okay, so maybe I should make that more explicit, though. So which problem are we looking at here?
Number 2 on homework 3. Yep.
Yeah, so Legendre polynomials. Legendre polynomials are defined over what domain, guys?
It's -1 to 1.
Okay, so our domain is -1 to 1. We need to know that because we're going to do integration. All right, so now we've got basically an integral from -1 to 1 of 1 times 1 dx. And then we're going to take the square root of that. You okay with that so far?
Yep.
So this is just x, right? Evaluated from 1 to -1 square root, which is what? It's 2, so it's root 2.
Yeah, just root 2.
Okay, so it's root 2. All right. So we get root 2 out of the, so the norm of the function 1 is root 2. Isn't that interesting? That's kind of cool. So that goes down here, root 2. All right, so our first Legendre polynomial is going to be 1 over root 2. And you okay with that? Okay, so that's we're done with the first line.
So I don't know if this is another oversight, but the Legendre polynomials have a scaling factor associated with them.
Yeah, they do. So once you finish, you'll see the scaling factor. So then you just keep going. N to, well, maybe I could, I don't want to do the whole problem. Do you kind of see how this works at least?
Yeah, that really cleared up a lot, so that helps a lot. Thank you.
Okay, so you can go through the rest of the algebra.
If we could just go 2 steps further, that'd help me.
2 steps further. Okay, so we've got, this is going to be n2 minus we do that right? That look good?
So the n here, the n2, when you're doing the projection, it says the projection is n1 bar, and you've wrote n1 in there. Is it supposed to be an n1 bar?
Let me see here.
Or orthogonal n1 bar? Is that
This is what I was talking about earlier. Those statements that you just made, Eric, those two statements are equivalent to each other.
Well, I don't see how they can be equivalent to each other. N1 over there on the top right is 1 over the square root of 2. And N1 bar orthogonal is equal to 1.
So if you substitute the definition of N1 into what Dr. Scott wrote there, and then simplify it so that it's in terms of N1 bar, you will get what Dr. Scott wrote in the notes.
Because there's 2 on the top and 2 on the bottom, and the square root 2's will cancel out.
But I think in the notes, I'd like to just do it in terms of, you're right, I mean, it doesn't matter, but.
What you'll find is the norms and the denominators will cancel out with each other.
Yeah.
So it's just a different path to the same answer?
Correct.
Okay.
Great, thank you. That's what will be. Okay. And then these inner products are again just integrals. So
Yeah, that's as far as you need to go. That's what I need to see. Thank you.
isn't it, I mean, like from my perspective, I'm always kind of fascinated how like these function spaces act just like Rn. You take a function, you take its norm or inner product. Like you can find the angle between functions and stuff like that. It's weird. Okay. Any other questions? So I guess on Monday, I'll take some time to go through this thing. I really want you to see the relationship between quadrature and polynomial interpolation, because from my perspective, I think that's a big light bulb that will help you understand a lot of what goes on in finite elements. So I'm going to take some time to go through that. And then we'll move on to an actual physical problem. We'll have like Young's modulus and stuff, which should make the engineers feel pretty good.
It already does. I'm excited for that.
Okay. Any last comments or questions? If not, we'll stop here.
I just have a last comment on like the homework. It looks like you moved a bunch of the problems from homework 1 to homework 3. I'm assuming that we've already done those. Like we don't need to do them again.
That is correct.
Okay.
Yeah. You guys are self-correcting. This is the reason that I'm making this class fairly easy to kind of self-guide, because there will be a lot of churn as we go through the material.
Kaylin, practice makes perfect.
Okay, well, let's finish there. I'll stick around for a few more minutes if anybody has anything else they want to talk about.
Just to clarify that, I didn't notice that till now. So was it problems 3 through 5 or 3 through 6 that got moved from homework 1 to homework 3?
It is everything that has to do with quadrature, because I moved quadrature from section 1 into section 3.
Oh, okay. Okay. So problem 6 is a new problem, even if you did do homework 1.
Yeah.
Okay. Perfect. Thank you.
Anything anybody wants to talk about, or are we done? Sounds like we're done. It's got to be Friday. Okay,
Yeah.
have a great.
Everybody's done with the week.
Yeah. Okay, have a great weekend, everybody.
Thank you. You
Bye.
too.